So I'd like to thank everybody for coming out to attend the dissertation defense of Zheming Zhou. Zheming has been as a PhD student at Michigan Robotics program here, our graduate program, and he's been here just as long as I've been at Michigan. So Zheming and I both started at Michigan in 2015. We were members of the Robotics Day committee together, which is where I first met him. And then we started working together during my first year, and it's just been we started working in reproducing Rob Platt's grasp localization, handle grasp localization routines, and we just had a lot of fun doing that. And so we continued moving on and doing more, producing a number of publications in terms of manipulation and grasping and clutter. And that led to interest in light field and plenoptic cameras that offer interesting new insights into how we can deal with transparent objects as well as many different other types of objects. But this dissertation really is focusing on the issues of transparency and translucency, which dominate our world in terms of glass, translucent objects, many different types of materials. And so I'm really proud to give the floor to Zheming, so we can talk about some of his work in this area and as well as give some insights for future directions. Zheming, the floor is yours.
Okay, so thank you for the introduction, Chad. So hello everyone, good afternoon. And my name is Zheming Zhou. I'm working with Professor Chad Jenkins at the University of Michigan. Today I'm very pleased to be here to present my dissertation defense. And I'm also very glad to have all of you here to join this talk. So my dissertation title is Robotic Manipulation under Transparency and Translucency from Light Field Sensing. So in the 1966, the first general purpose robot Shaky came into the world. It can perform actions like navigating in an environment with obstacle avoidance and moving objects around by high-level commands. So 50 years after the born of the Shaky, we have seen much more advanced robots, and they can perform more complicated tasks in our daily lives. For instance, robots can deliver goods to a front door, solve items in the warehouse, they can help assemble parts in the factory, and they can even serve drinks for you as a bartender. So in order to successfully perform all those tasks, robotic manipulation is inevitable. Also, robot cannot act if it cannot see. The vision perception systems becomes a very critical part in robotic manipulation, and it remains a very challenging problem in the robotics area. For instance, here we have listed several manipulation pipelines with vision perception systems, and all of those methods either need depth or RGB information, or both of them. However, the RGB perception for manipulation is still not able to handle a lot of scenarios, scenarios in our real lives. For instance, if you get a home assistant robot and ask your robot to serve drinks for you, or even more, for instance, to build a champagne tower for you, so can our robot with RGBD perception do that? I'm afraid that is really, really difficult. So this is a video showing a more simpler scenario. So in this video, a KUKA robot tries to serve a drink by pouring beer into a glass. So if you look closer, you can see that because of the misalignment between the glass and the beer, the robot is actually pouring the beer directly into the sink. It's actually pouring into middle of nowhere. So it was close, but I may prefer the robot directly handle the beer to me, like next time. Then the question becomes, what is exactly the challenge that transparent object bring to the RGBD perception? The challenges are mainly twofold, we can see. The first is in the depth domain. Here is an example. We show a tabletop point cloud captured by a depth camera. There are actually 5 transparent objects in the thing, but none of their depths can be correctly captured. Secondly, a lot of obviously robotics perception pipelines assume that an object needs a reliable or invariant RGB features for recognition and localization, but the specularity and the distortions from transparencies will break many of those assumptions. Instead, To deal with those challenges, in this dissertation, we explore the use of live field sensing to enable robots to perform manipulation tasks under transparency and translucency. More specifically, in today's talk, I will introduce 3 methods in addressing the challenge brought by the transparency and the translucency under different environment setup and task complexity. The first work, PMCL, is short for Plenoptic Monte Carlo localization, which enables robots to estimate single transparent object 6-degree freedom pose under uncluttered environment. The second work, Glass Lock, aims to enable robots perform grasp actions like under transparent clutter using discriminative grasp pose detector. Third work, LIT, leveraged the advantage from both generative and the discriminative method to perform fast transparent object segmentation and the localization. More specifically, the generative here refers to the sampling-based method, and the discriminative here means learning-based method. And the word light field and the Plenoptic can use interchangeably during this talk. So let me introduce the PMCL first. The objective of PMCL is to estimate single object 6-degree freedom pose under transparency and translucency. In PMCL, we propose a novel Plenoptic depth descriptor called DLV, or depth likely volume. With PMCL, our robot can, for example, pick up 1 cup from the sink with running water and place on the tray. So in this work, we explicitly tackle the perception challenge brought by transparency in depth domain. Here we give another example showing a depth observations from RGBD sensor mounted on the top of our robot. It is obvious that the transparent cup in the water sink is totally missing from the sensor. If we can incorporate the RGB information, we can see some clues here, but still, robot is not able to interact with them because the distance, or we see that the depth information is missing. Instead, live field perception shows some promising results in dealing with a transparent object. The top 2 works are trying to recovering the depth for reflective surface or even the object behind the translucent surfaces in a simulated environment. Live field in robotics is still limited, but there are also shown promising results in underwater reconstruction and the reflective object localizations in 2D plane, as illustrated in this following 2 works. So build on those insights. In this work, we have proposed a depth likelihood volume, or DLV, as a volumetric Plenoptic descriptor to represent depth as a likelihood function rather than a determinate depth value. So to better understand this, here we give an example of a thing with a transparent cup laid on an opaque table, and we divide the space into grid cells. Then we will show how the depths will distribute in this new representation. We start the cell from the top, which is a minimum depth, and in the bottom left corner, we will show the relationship between the likelihood and the depth. When cells moves down, we will observe 2 peaks in depth domain. The first corresponding to the top surface of transparent cup, and the second is correspond to the top surface of opaque table. And the likelihood is proportional to the opacity of the surface. Then the question becomes why that happens and how can we calculate this representation from live field observation? Here we give an intuitive explanation. We continue with the setup that a transparent cup lay on an opaque table, and we divide the space into grid cells. We assume that each grid is independent and emitting light in different directions. Then we can investigate light ray consistencies in different directions under this scenario. For example, for this blue cell, there is no actual surface on it. What you really get is a light ray that coming from the different surfaces. It comes from opaque table, it comes from the transparent cup, or any other things they put on the table. In that regard, it will show almost no consistency. But if we look at the cell that from the opaque table, then it is an opposite way, since all the light directions will be very consistent because of the Lambert diffusion of the surface of the opaque table. Things becomes more interesting if we look at the transparent object. Apart from its own diffusions, the light ray emitting from the transparent surface will add with the light rays coming beneath it. What that means is it will show some consistency, but not as much as like the opaque surfaces. So if we rank the consistency of these three cells, we will get a relationship illustrated in the bottom left corner. And so opaque go first, transparent go next, then is no surfaces. Or we can see it's like absolute transparent. So then the question becomes like, how can we calculate those light directions? We know that for a conventional RGB camera we are using, for instance, it's currently focused on the this yellow cell. All the light direction, like light rays emitting from that cell, will be focused by the main lens and be captured by a specific sensor on the sensor plane. So during this process, the light ray direction information is missing because we are kind of integral over all the light ray directions and only capture the intensity of that light ray. So our conventional camera can only capture the intensity of the light ray. So the light field camera, or here we referring to the micro lens or lens lit based light field camera, did one step more by adding another layer of what we call the micro lens layer between the sensor layer and the micro lens layer, and it is put on the focal distance. So then if we investigate the same three light that coming from the cell, then we can see that the sensor is still captured the intensity information of the light ray, but because of the relative position between the micro lens and the sensor plane, we are also actually captured the direction of the light. So things we are talking about the light field camera and the light field. So let me talk a little bit background of the two things. So we know that a sensor can capture intensity of that light ray, which is indicated as like yellow sensor here. Then we can describe the direction of light by using two virtual parallel plane, and one is intersect with the main lens, and the other is intersect with micro lens. Then we can use the intersection point between the light ray and these two virtual parallel plane to describe the direction information of that light. So this is what we call 4D light field parameterization that proposed by Mack and Pat back to 1996. So the first four variables, UV, ST, is describe the direction informations of light ray, and the lambda is describe the intensity, or we call the frequency of light ray. In the robotics applications, we normally describe it using RGB3 channels to describe the light ray. So notably, since it has like two planes to describe the direction information, so different planes has its own meaning and the resolution in the physical light field camera. The first is UV plane, which is what we call angular resolution. So that describes how many number of light directions is actually captured by this light field camera for a specific physical point in the real world. And the second definite resolution is what we call the spatial resolution. And the spatial resolution's definition is more similar with our conventional RGB camera's definition. It basically tells you how many number of physical points I'm capturing for the real world. So here we show an example of a real life image. So if we take a closer look, we can see those rectangle-like features. So if we remember what we have talked about, the angular resolution, so within those small rectangles, it's actually capturing a bunch of, obviously capturing various of light directions for a specific point in the real world. For instance, for this example, it's actually captured the 14 by 14, like 200 light direction for a specific point in the real world. But it is not that intuitive if we decomposited the image like this way. So a more, I would say, intuitive decomposition of a 4D light field image is to decompose the light field image into a 2D array of 2D conventional 2D images, which is what we call subaperture image. Subarbitrary image can be interpreted as multi-view image of a same thing with a camera array on the same plane, and with a uniformly sampled the light rays coming from the scene. So we will see that a very commercial use of a live view camera is to perform image refocusing even after the image has been taken. So we can see that we can focus on any distance even after the one live view image has been taken, which is cannot be achieved by the conventional camera. So live view camera enables us to capture the light direction information, and we can use this information to construct a new light field descriptor, DLV, or depth like a volume. So we first we give it an example to investigate a specific point P in the 3D space. So our likelihood for the P can be calculated this way. We first hypothesize it's emitting lighting, and then we can use the ray recasting to find its corresponding hitting point in the different subarbitrary images. Then we define what we call the similarity cost for that point and the different light rays that are coming from it. So basically, we compare the similarity of the light rays emitting from this assumption physical point, and then we can calculate it under the color space and also the color gradient space. Then we have another normalization terms to normalize the whole likelihood to the range from 0 to 1 to be a likelihood for the pixel to have some level of the depth in it. So after we have depth likelihood volume constructed, then our object 6-degree freedom pose estimation problems can be formalized this way. So we are given an object mesh model M, and definitely we predefined grasp poses on it. And then we given a live field observation O. So the target is we want to find an object 6-degree freedom pose Q that can argue max the possibility of Q given the observation. After we find that maximum ROC belief, then we can transform the pre-grasp pose to the observations to enable robot to perform motion planning and the manipulation. So to solve this objective function, we use Monte Carlo localization method or iterative particle optimization method. Each particle here represents a hypothesized 6-degree freedom pose. And we can plug into our likelihood function to calculate its corresponding likelihood. So the likelihood is calculated by plugging to query each rendered depth in the depth likelihood volumes and to calculate the whole likelihood for the particle. So here we have shown an animation of particle convergence process. The left image is all hypothesized, while the right one is the most possible poses. And we can see that after several iterations of convergence, it can converge to its maximum belief pose, which is very close to our ground truth pose. Here we shown another examples of estimate an opaque object behind one layer of a translucent surface. So we can see that it can also get a decent result in that scenario with our method. After we got the object 6-degree freedom pose, then we can transform the predefined grasp poses to the target object and perform grasping. Here we show an example of a robot successfully pick a transparent cup from the sink with running water and place on the tray. Here we show another examples of a robot successfully pick up bleach bottles from the water tank and place on the table.
Can I ask a question?
Sure.
Let me know if you want to reserve questions to the end. What I was going to ask was that I just want to verify my understanding that we're not reconstructing the point cloud here. We're just we're inferring pose directly from this
representation depth cycle volume. Yes.
Yes.
Okay.
That's the word. That's the phrase I was looking for. Thank you.
Yeah.
Let me just add to that. You say you're getting a 6-degree of freedom pose, but you have a symmetric object. Doesn't that imply that there's an inconsistency?
Okay, so that in the later in our evaluation step, we explicitly talking about how we evaluate the symmetric things. Because for manipulation, when we generating the pre-grasp poses, we generating the grasp poses, I will see in all directions, and then when we get the 6-degree of freedom pose estimations, yeah, it's losing kind of 1 degree of freedoms, but still we can transform the grasp poses and send to the manipulation pipeline to filtering out which kind of grasp poses is graspable. So yeah, in the pose estimation stage, we will see we still estimated the pose in 6-degree of freedoms, but it's in the rotational symmetric degree that we are considering that it's always correct, no matter which rotation.
So you're really only doing 5 degrees of freedom then?
For the symmetric object, yes. So we will see in our following works, we are extended to 4 6-degree of freedom pose that is not rotational symmetric. So.
And have you run it on full 6-degree of freedom non-symmetric objects?
We do have, like we have glass jars. It's
okay. Okay.
Yeah, it's not the full. Yeah. Okay. Yeah. And quantitatively evaluate our methods, we design a small data set in the kind of time, and it's have 2 type of category things. The first is transparent objects, and we also have an opaque object behind the translucent surfaces. And for each thing, we have designed 6 test things, and for each test cases, we run 10 trials. Since the object we using in this project is a rotational symmetric, as we mentioned before, so we use the dot product between the estimated pose and the rotation, and also the ground truth pose as an evaluation metric. And during our manipulation stage, we want to separating both the the positive one and the negative one out, because in our manipulation, even the object are flipped, we can still get the grasping in these cases. So we just want to separate in these 2 cases. And here is the result for a single transparent object cases. We can see that in the plot, the title is translation arrow bound. It's 2 centimeter, and for the x-axis is the dot product between the ground truth and the estimation. And the y-axis is the correct pose. So basically it tells you like in this percentage, it's within this dot product. For transparent object, we can get in 92 accuracy rate given 2 centimeter rotation, a translation bound and a 10-degree rotation arrow, and there is no flipping cases. For the object behind the 1 layer of translucent surface, we get 87 accuracy rate, but there are 5% of estimated poses are actually flipped in these cases. So while PMC, the first work, can perform object pose estimation under transparent environment, it also has several limitations. So generative method is often time consuming, need object models. Also, when things becomes more and more clever, it will be hard to localize specific objects. Instead, for a simple manipulation task like pick and place, we propose a glass lock as a discriminative pose detection method. Different from the 6-degree freedom pose estimation method, which transformed grasp pose from local coordinate frame to observation, grasp pose detection focuses on local geometric features to indicating whether it is graspable or not. So the objective of glass lock is to detect feasible grasp poses from transparent clutter, and then we perform object pick and place actions from using the glass lock. The glass lock problem formulation is this way. We given an object we given a series of live field observation O from 1 to n, and we want to find a set of n factor 6-degree freedom pose GV that can indicating a good grasping. For instance, if we have a transparent cup in the thing, we want our algorithms to generating those sampled grasp poses, and we want our algorithm to verify like which one is feasible and which one is not. For instance, the middle one is collided with the transparent cup, so it's not valid. And also for a valid one, we also want to associate them with confidence score to send to a robot to do the ranking. So our glass log pipeline has 2 stages. The first stage is what we call multi-view DLV construction stage. And the second stage is what we call grasp pose detection stage. So let me introduce the first stage. The multi-view DLV construction stage is very much like the single view DLV construction, but because we are introducing the different viewpoints, then we can perform the ray recasting to different view angles and get more investigations of those light rays. But the benefit of doing that is not only we have more data, but also because we have large baselines, and it will give us a chance to perform what we call specularity reduction. We know that for transparent surfaces, it also have a non-Lambertian property, which means it will have a specularity. And in different angles, the specularity behavior will be vary a lot. So we can looking at the variance of those view angles about specific light rays that we capturing, and if it is saturated, and then we can using these features to eliminate those saturated colors to reduce the noise that introduced by specularity. In this case, it's one construct that depth like a volume. After we have a DLV constructed, then we can went to the second stage, which is what we call grasp pose detection stage. In the grasp pose detection stage, the first step is perform grasp pose sampling. And since we are sampled the grasp pose, then we first need to know what kind of gripper we are using. For instance, we are using the for progress fetch robot, which have a parallel jaw gripper. Then what we defined what we call grasp volumes to be a space when the robot fingers close, it's a swept volume. So it's a box-like volumes. Then we can sample the grasp pose in the DLVs, and for each grasp pose, we extract its local DLV features. And instead of using the 4D, 3D DLV as a feature, we also project it into 3 axis to be a 2D feature to represent the corresponding grasp poses. Then we have trained the small classifiers. So it's basically a multi-layer perceptron, and it will tells you like which grasp pose is actually graspable and which one is not graspable. Then also associate with a confidence score in that cases. It's a confidence score in that cases. So, and then we can pick the graspable poses with the highest confidence score and send a robot to perform grasping. So here we show an example of a robot successfully pick up a plastic cup from the table and place on the tray. And we mentioned that we have trained a small classifier to perform the grasp pose detection. So here we introduce a little bit about how we generating the training data for that DLV training. So basically we using 2 training objects, and later on we're testing on 5 different objects. So which means we have a novel object in that cases. To generate the training data, we first put the transparent cup on the table and take 1 shot of live view image. Then we construct the DLVs for the same. And the second step is we mask the transparent cups with opaque table and try to put on the same locations and with the same poses. And then we use the RGBD camera to take a 1 shot of the view, especially we want to take the point cloud, and then use the point cloud based grasp pose detection algorithms to generate both the negative samples and the positive samples. Then we can project those poses back to our DLVs to extract its corresponding features to be training data for both the positive samples and the negative samples. And to evaluate our glass log algorithms, we use 5 different transparent objects, and we formalize like 8 different things with a different number of objects and the different clutterness of objects. And we use, and for each grasp I would say for each graspable trials, we perform 10 grasping trials, and for each thing we perform we use like object grasp percentage as an evaluation metric. For instance, for thing A, it tells you like for it have 2 objects in the thing, and we perform 10 manipulation trials, and the total object grasp percentage is 0.7, means over 20 manipulation trials, we successfully pick up 14 number of objects. Also, we show object-wise grasping successful rate, and we can see that over I would say 220 trials, graspable trials, we can get overall 81% of our graspable successful rate. So in the end, I want to for the glass lock, I want to show some qualitative results showing our robot perform tabletop cleaning task by picking and place transparent objects from the clutter. While glass lock is able to perform pick and place grasp post detection directly from DLV, there are also limitations for glass lock. First of all, it's only limited to simple pick and place actions because it's not actually know like what kind of object it's grasping, because it's only looking at the local graspable features in the DLV. And also we mentioned that when generating training data, it's really time consuming, and we'll introduce extra errors if the opaque object is not placed obviously in the same position or in the same pose as transparent objects, then it will like introduce errors during the training step. So build on those insights, I will see in our third work LIT, we leverage the discriminative and the generative method for transparent object segmentations and localization. So the objective of the LIT is to perform transparent object segmentation and the 6-degree freedom pose estimations, and for more clutters, obviously for more challenging things, and then we enable robot perform robot manipulations under those scenarios. So both PMCL and the glass lock focuses on the challenge of perception in depth domain. But for the more complicated task, for example, the robot bartender, the robot needs to recognize and localize, like where is a beer and where is a wine cup. So in that regard, the specularity and the distortions from the transparency in RGB domain can be turned into a feature to recognize those objects. So before we dive into details of the LIT framework, let me give you some examples of how light field capture the reflection and the refraction features in the RGB domain. So first is a reflection. So here I have shown 2 images taken from a convention RGB camera. So convention RGB camera. Could you distinguish like which is paper and which is sky? So you can type numbers in our chat channels. If you think the first one is paper, you can put 1 there. If you think the second one is paper, then you can type 2 there. I will give 20 seconds on that. Actually, I saw a mixing of 1 or 2. Actually, 2 is the majority, I believe. That
I would agree. I see 2 as the majority vote. Yeah.
Yeah. So that's a reason. So even with the same, I would say, observations, I believe our human brain is more superior in the reasoning part to how to distinguish them. So even given those 2 identical things, so I would say it is kind of pretty hard to distinguish which one is paper and which one is sky. That if you only looking at those images, but I will give an answer later on. But let me first introduce if we using the live field camera to take a look at the thing, what will be different? So if we use a live field camera to take the same object, then we can see some clues here. If the right image, if you take a look at the right image, you can see those rectangle-like feature patterns So if you remember, in those small boxes, it's actually capturing the different light directions. So the same patterns still existed in the left image, but because of the light directions in the same rectangle is too uniformly distributed. So you cannot distinguish those boundaries for each cell. So connecting with our knowledge that the skylight is more uniformly distributed, while the paper, because of the surface reflection property, will be a little bit different, then we can see that the second one is actually the paper, yeah, and the first one is sky. So majority is wing here. And yes, apart from the reflection, live view camera can also capture the distortion features. We know that if we take a multi-view image of an opaque object and put it into an epipolar image stock, we can observe those straight lines, which is indicating the depth of the camera. It's an epipolar image, right? So, however, if there is a refractive object, it will distort the background object, which will produce like curves in the epipolar image space. So this definitely could be a feature to distinguish the transparent objects, especially for those have a curves, can generating the refraction features. So both the reflection and refraction features can be potentially captured by the live view camera, and build on those insights, we propose we introduced our LIT framework with a LIT network as a first stage. So LIT network inputs a live view image, and it's outputting the object semantic segmentations, object labels, and also the object center predictions. So for LIT network, we first feed into a subarbitrary image stock, and then it will went through what we call live view filters. So we design live view filters is actually a learnable 3D convolutional layer, and each of which is dealing with different features in the live view image, epipolar image space. So for instance, the EPI filters, which is short for epipolar image filters, is more looking at the refraction features in the epipolar image domain, while the angular filter is more focuses on the specific cells that within the light direction space. So it's more capturing the reflection features. And after the live view images go through those 3D learnable 3D convolution layers, we concatenate those features together to be a giant live view features, and went through layers of encoders here and encoders layer. And then we have two branch of decoder layer. The first decoder network is outputting the object semantic segmentations, object labels. And also the second stage is output the object center prediction. So basically, in the first stage, if one pixel belongs to a transparent object, it will be voting like who is my center in that cases, then generating the second branch output. So after we have a LIT network gives us object semantic segmentation results, labels, center predictions, then we can pass it to the second stage, what we call LIT generative inference stage. So it will output the object 60-degree freedom pose in that cases. So each predicted centers will be prior to initialize the particles in that cases. And for example, here we directly initialize like 5 transparent champagne cups in these scenarios and performing the localizations at the same time. And after it reaches our convergence criteria, we can see that it is converged to its maximum BD poses, and it's very close to our ground truth pose in that cases at the same time. So here is the overview of our LIT framework. But we know that for the first stage, LIT network, it's actually a very giant network with 3D convolutional layers, need a lot of parameter to train. And we cannot do something like we did like previously in the glass log to do like manual capturing and manual labeling, because that will be too time consuming. So incorporating with the LIT network, we also propose a ProLIT dataset. ProLIT dataset have a training dataset, training and testing set. For the training set, it's a pure synthetic live field training dataset, which have 5 transparent and translucent objects, and it's incorporate it has like 15,000 training objects, images per object. And for the testing set, we have the same number of objects, but we have 300 images with object segmentations, labels, and the 6-degree of freedom pose manually labeled by ourselves. And here we show examples of how we generate those synthetic images. So we build a customized live field rendering and image generation pipeline built on Unreal Engine with the data auto labeling toolbox. So we perform domain randomizations, randomize the light, the environment, and also the object pose, camera pose to generate those live field images. So here we show some qualitative result, that we can see that even under a very challenging environment, we can get a very promising result. If you look at the bottom right corner, so even in a lot of refraction features, we can still accurately localize those objects. So to quantitatively evaluate our LIT, we compare LIT against four state-of-art methods with different sensor modalities. So the first we compare with a clear grasp, which is a state-of-art transparent object depth completion method. And also we compare with DOPE, which is state-of-art general purpose end-to-end object process meter. We also compare with augmented autoencoder, or we call AAE, which is state-of-art textureless object process meter. And definitely we also compare with PMCR, which is a generative live field-based transparent process meter. So we use ADDS as an evaluation metric to evaluate our method against all those methods. So we use area under the curve, or AUC, to compare all the methods. In the plots, the x-axis is the distance threshold, and the y-axis is accuracy. So basically, it tells you within those distance threshold, how much percent of the object is within the accuracy. So we can see that the LIT can overperform all other methods for all test objects. So then we further ask ourselves this question: what is actually the benefit of using live field over like RGBD perception over transparent and translucent objects? So our one observation is, obviously, all those RGBD-based methods need a kind of opaque background to infer or extract contour informations of transparent object, because they are kind of doing a binary classification. If it's in-value readings, it's transparent object. If it's not, then it's not a transparent object. While the live field camera don't have these limitations because it directly look at the surface reflection properties in the light direction domain. So to further investigate this observation, we further separate the testing scenes into two categories. So the first is opaque background category. Under this category, we can see that all the tested scenes can provide smooth and valid depth readings for RGBD camera. So the second category is what we call a challenging background. So under those scenarios, because of the surface its own reflectivity or other issues, it will generating large areas of invalid readings from the depth camera. And in that cases. And I think all those things are also very common in our daily lives. So first, let's take a look at the opaque background results. So we use the same evaluation metric, area under the curve, to evaluate all 5 methods. We can see that under opaque background, our LIT still performs best, but the clear grasp, which is RGBD, one of the RGBD methods, can perform comparably well or even better for some object in the opaque background scene. So things becomes more interesting if we look at the challenging background scenes, then we can see the benefit of using the live field camera. So here's the result of the challenging background. We can see that live field methods, so both LIT and the PMCR, I will see, performs comparably well in these cases. And if you look at like the blue lines and the orange lines in this scenario. So both of them performs like much better than the RGBD based method in that cases. So in conclusion, we can see that overall, our method LIT can still overperform RGBD method in both things for tabletop transparency object approximation. But I will see the live view methods establish a less sensitive to the background changes, while the RGBD-based methods are more reliant on those features. And we can see that for an opaque background scenario, and we can see that RGBD method can perform comparatively well or even better for some objects. So in the end, we want to show a Champagne Tower demonstration. So basically, we use our LIT framework and enable the robot to perform transparent object pose estimation. And then we only give the robot like where to place them, and the robot can successfully pick and place all the transparent champagne cups from an opaque table and place on them as a champagne tower. So that's me to pouring the champagnes. I may better to also let the robot do that, but it's kind of too heavy for the robot arm a little bit when it's for. Not expert as a robot, maybe 10 years later. Cheers. So in the end, I want to see in this dissertation talk, we have introduced 3 methods to enable robots in performing manipulation on the transparency and the translucencies using live field sensing under different thing, I will see environment setup and the thing completeness and the different purposes. And our initial explorations also give a lot of future directions that warrant further investigation. For instance, one of the biggest limitations of live field-based method is time computation, I would say computation cost. Because from this table, we can see that live field method takes much more computation time than RGBD method because of like one live field image is easily reaches like 100 or 200 or maybe like 500 or 1,000 size larger than the conventional RGBD images. So if we can construct a more data efficient live field representation and its descriptor, then we can extend our work to a more real-time implementation. So recent work called a neural radius field or NERV give us a really good insight of how to build a data efficient live field representation. So NERV proposed a neural network that with a 5-dimension input, XYZ, theta phi, and it's outputting the RGB and the sigma. So the XYZ theta phi is basically tells you the directions of the light, obviously light rays. And if we look at the 7D live field functions, we can see those similar things sharing with them. So basically the XYZ alpha beta is exactly the XYZ theta phi in the NERV function. And if we only consider the static thing, which we can eliminate time t, then we further decompose the lambda into like RGB. We can see it's pretty similar between those two functions. And the only difference is sigma, or what we call the density. So in original paper, the density is a value along a light ray that indicated a color density. And in most cases, the density is highly correlated with appearance of opaque surfaces as illustrated in this plot. So this is actually very similar with our DLV representations, while we also take transparency and the translucency into this consideration. So from this point of view, we can think of NERV as learning a neural network representation or function approximation of light fields and concurrently learn DLV similar features in this scenario. So if we can incorporating those inspirations with our dissertation work, we can think of several future directions that indicated in these slides. And we believe there are a lot of potentials of using light field perceptions in robotics in the future. And here we have listed several publications that support all the materials we have covered in today's defense talk. And in the end, I want to first express my appreciations to all my committee members, and thank you all for joining this talk and give me constructive feedbacks and helps in completion of this dissertation. And also I would like to thank all my collaborators and the lab mates. Without their help, all those works are impossible. Also, I want to say thank you to all the staffs in our robotics programs, Denise, Kim, Damon, Dan, so a lot of you. I joined the programs, as Chad said, 2015, and as a master's student. So all those years, I feel so proud of to be a member of Michigan Robotics, and thank you all for your help during all those years. And then definitely, I want to thank my fiancée Jiahui. Thank you for always being there for me through all those years, and regardless the physical distance we have in the previous few years. And last but not least, I would like to thank my parents for their unreserved love and supporting my life. And I cannot be what I am today without their support. So at this time, I would like to thank you again for joining this talk, and hope the robot can help everyone in every aspect of life in the near future. Thank you. Cheers.
All right, thank you very much. Yay, please feel free to unmute if you'd like, and show our appreciation.
Thank you.